I'm Courtney. Like Rachel said, I'm a postdoc at UCID, where I've been for 2.5 years. And I'm going to talk to you about something that I've been working on for, I want to say like 8 years now at this point, which is the hydrogen-deficient carbon stars, which are a star that people don't generally know about all that much, but I think are very interesting. And in particular, I'm going to talk about two specific projects that I've been working on recently, which are some advances that we've got in the formation process and also in the dust production and dust properties of these stars. So to start, I'm going to give you the long rap sheet, and I'm actually just not going to spend that much time on this because I'm going to go through each of them in detail, but I think the point that I want to get across to you with giving you this giant bullet list of information is that these stars are really strange. And they're strange in a lot of ways. So they're strange by name. You know, they're hydrogen deficient, as the name suggests, less than 1% hydrogen by mass, which is quite deficient. And they're also carbon rich, so their C over O is 1. You can see they have these lovely spectra here that you can see, and all these other interesting properties over here. And I'll go through most of them in detail, so don't worry if you can't read them all. I actually want to start by saying there are two major types of HDC, and you'll hear me talk about both of them a lot during this talk, so I wanted to start here. The main one that everyone knows about, or more people know about, is the R Coronae Borealis variables, or the RCBs. These are known famously for producing dust, so here I have a light curve of R Coronae Borealis itself. You can see that it's a 6 magnitude star, but this randomly in 2007, it went down to 15 mags. That's a nearly 9 mag decline. And this decline itself lasted for about 12 years and has all these different structural events inside of it. Whereas there's this other set of stars, the dustless HDC stars. As the name suggests, they're the same spectroscopically. They don't produce dust. And we don't necessarily know why that is, and that's sort of a major topic of research these days. Both of these stars are particularly strange in that they have very small oxygen isotopic ratios. So they have a lot of oxygen 18, which is a strange isotope to see. They have generally between 1 and 10 and less than 1 for the dustless HDCs. They're also variable at maximum light, which I'll talk a little bit about in a minute, and they have different variation timescales on there. Generally speaking, we know of about 200 of these stars total in the galaxy and in the Magellanic Clouds. But actually I've lied to you because there's actually kind of 4 types of HDC. Now, I'm not going to talk a whole lot about the other 2, but you will see their names come up a few times, and so I just wanted to be clear that there are actually a couple more. And rather than reading all of this, I'll give you an HR diagram, which is much easier for everyone. So here, up in the supergiant region of the HR diagram, we've got the R Coronae, which form this kind of box here, the dLHdCs, which are mostly overlapping with these stars. We've got the Dewey-Percy variables, which are believed to be like cold R Coronae, and I'll talk more about that later. And we have the extreme helium stars over here, which are like warmer versions of the R Coronae in a way. Now, the extreme helium stars are also carbon rich. It's just that they're warm, so you see helium lines instead of carbon molecules, and so it's weird to call them an HDC a little bit, but we live and we learn. These are my friends here, the R Coronae and the dLHdCs. I'm going to talk mostly about these. And like I said, you will see the other 2, so don't get confused. Just know that they're related, but we don't actually know how related they are. We just think that they are probably related in some way. So a typical HDC spectrum is quite unique, and I understand probably not everyone deals with spectroscopy all the time, so I've pointed out the important parts here, which are that here's a warm star on the warm end of the HDCs, and here's a cool star over here on the right. So the warm star has a lot less molecular features, but you can see it actually still has a pretty weak C2 band feature here, which is quite rare for such a warm star. We've got the usual suspects. We've got these calcium-2 H and K lines and the calcium-2 triplet. These are seen in almost every optical spectrum around this temperature. But you can also see there's no H alpha, right? This is around an F-type star or A-type star. They should have very strong H alpha and a Balmer jump here, but they have neither. And for this one, we can also see it's a bit off the edge here, but we have some S process lines as well, so this is case variant 2. For the cool ones, the spectrum is a lot more interesting. We've got these big, beautiful C2 bands here in the blue, and we've got these lovely CN bands here in the red. Again, we have the H and Ks, the calcium-2 triplet. You can see as well there's no CH, which is what you would see in a cool star like this around a G type. And we also, again, see no H alpha. But here in the cool stars, you can also see some other S-processed elements, such as strontium-2 here, and there's a couple other barium lines and things like that throughout the spectrum. So they look really weird, and if you saw one in your spectrum, if you took a spectrum of a star and you saw this, you would say, what the heck is that? And that's what these are. So like I said, we have S-process lines in a lot of the spectra, and in fact, nearly all HDC stars show signs of S-processing. This probably tells us something about the progenitor star's evolution on the AGB. We'll get to the formation stuff later, but this probably tells us something about an AGB process that happened much earlier in its life. That being said, there's been almost no studies of this, and S-process is not even really mentioned a whole lot, except that in 2022, I looked at the whole sample of stars and found that there was actually a subset here of these 6 stars that have particularly strong strontium-2 lines at 4077 angstroms. So here's an image of what they look like in the spectrum. So what I mean by especially strong is that these lines are almost as strong or stronger than the calcium H and K lines, which should be some of the strongest lines in a stellar spectrum. Compared to this kind of star down here, which is a bit more normal, which does have a strontium line, but it's much harder to see in this sort of smaller scale. So there's a bunch of stars here that have particularly strong light S-process elements, but what's interesting as well for these stars is that for these same 6 stars, except for A166, my stellar nemesis, they don't have particularly strong barium lines. So they are specifically enhanced in the light S-process elements. And from talking to Amanda, this probably also has something to do with the way the HEB star evolved before we got here. And so there's a lot of really interesting stuff deep within the spectral analysis that we just haven't gotten to yet in studying these. I talked about oxygen-18 a little bit earlier, and like I said, oxygen-18 is a rare isotope that you don't generally see. So the solar oxygen-16 to 18 ratio is about 500, and for these stars, they're on the order of 1 and going up to about 10, but all HDC stars that we've looked at show strongly enhanced oxygen-18. So here I have an infrared spectrum where you can see the CO bands, and the black ones here are the oxygen-16 CO bands, and the blue ones here are the oxygen-18 CO bands. You can see that there's a very stronger than most stars, 18O band here that you can see very obviously, and these ones here, which are just generally not common to see in these kinds of spectrum. Now what's interesting about oxygen-18 is that this actually serves as sort of a smoking gun for our formation mechanism, which I've alluded to, in that there was a long time where people were wondering what was forming these. Are they like some kind of weird post-AGB star? Are they like a very late thermal pulse? The model in literature was called the final flash model. But once we found the oxygen-18, we actually sort of converged on the idea that these are formed by double-white-dwarf mergers, wherein you have a carbon-oxygen white dwarf and a helium white dwarf which merged with each other and form a new stellar object that then evolves up to supergiant radius. And the reason for this is that, the reason we think this at least is that double white dwarf mergers, when we do the modeling, are one of the only processes that can create this amount of oxygen-18 without immediately also converting it into 22 neon via helium capture. And so oxygen-18 is a really important isotope for us. HDCs are generally located in the regions you might expect, which is the bulge in the disk, generally speaking, but we actually see them a lot more spread out than you would maybe think. And that was surprising to us when we looked through the Gaia data and tried to look at where all the stars are. In fact, if you look in the kinematic regions, we actually see them in all of the kinematic regions, which is sort of just not what we expected, because we would have expected them to see them in mostly these denser regions where you have a lot of stars. But the problem with this kind of analysis is that actually, since some of the stars produce dust, Gaia actually really struggles with a lot of these stars. And so Gaia DR4 will actually expand this a lot more. And that's actually why you see so many stars here which are grayed out, which is because they had some kind of dust event during the Gaia observations. And so the Gaia observations are essentially not useless, but not very good. But DR4 will be really helpful for us. And if you're interested in what Gaia does with dusty stars, then you can ask me later and I'll talk about that. These stars are varying of some kind at maximum light, but the question that has been coming up and the question that I wanted to answer in my postdoc, and I'm still kind of working on, is are these stars pulsating or are they varying? So historically we use pulsation to mean any kind of variability at maximum light, but these days we tend to use pulsating to mean that specifically there's like a standing wave within the star of which we can do astroseismology on, for example. But it's not clear for all of these stars whether or not the variation at maximum light comes from pulsations, i.e. an actual standing wave, or if it's differing brightness signals from the surface convection, wherein the surface convective cells have differing brightnesses and change the brightness of the star, which is seen in like the sun and in red giants and other things. And it may very well be true, and this is a common theme for HDCs at least, that it may be true that they do both. So here's a light curve here from WAVSO of R Coronae itself, where you can see that it's clearly varying, but it doesn't necessarily look periodic. And in fact, it looks a lot like what the stochastic variables look like. I know Maya was here 2 weeks ago, and she talked about stochastic variability, and this looks very similar to that. But then there's two over here clear examples using radial velocities where, at least for RY Sag, it's very obvious that that star is pulsating, actually oscillating, has this big standing wave. And there's many other stars where they claim to have found pulsations as well. And so this is still an open question and something that I am in particular very interested in exploring in the future, but I have to say we just haven't gotten there yet. One of the final things that I want to mention just as a review of these stars is that it's actually really hard to measure the temperatures of these stars because we have really bad atmospheres, and so doing spectroscopy is a little bit difficult. So what we've done instead is we've done a spectral classification system wherein we have the 8 temperature classes here, where you can see the warm ones at the top and the cold ones at the bottom, and they have a very lovely distribution of spectral appearances. And so we can and will, throughout the talk, be using these as a temperature proxy, which has been really helpful for us studying them and has really, really opened the doors for us to do a lot more analysis of these. This spectral classification system also has a range of carbon molecular strengths. So this was taken directly from the way that carbon stars are classified, where you have the temperature classification and then you have the carbon band molecular strength as well, rather than something like a luminosity class as you would get in the regular MK system. And something that's been nice is that this past year I've had a few undergraduates working on looking at the spectral classifications of stars and showing that the classification, so the spectral appearance, is robust to pulsations. So there's actually kind of we were hoping and praying that when we do the spectral classification and the stars pulsate or change brightness, that they don't change too much temperature too much, so they maybe don't move between these two spectral types over a pulsation cycle. And I've had some undergrads who've shown that that doesn't happen, so that's good. We're robust to that, which has been really good for me. So we're back here to our rap sheet, and I've gone through most of it, and if you don't remember all of it, that's totally okay. But what I really want to get across is that these have a storied history, and it might sound like people are working on these all the time, but they really aren't, and there's really not that many people working on them. And so a lot of things are like, we don't know what's going on, and hopefully in a few years we will get to it. But I haven't talked in particular about these two things here at the bottom, which are going to be the rest of the talk. The first one being that they are formed by double-white-dwarf merger. Now I did mention this, but I'll talk more about it in just a minute. And then also I'm going to talk about the dust production of some of these stars. So the first part that I want to talk about is the formation. And the question that we wanted to answer with this project was, can we explain the difference between R Coronae and dLHdCs, so the dusty and not dusty stars, with just a formation mechanism argument. So as I said, there are two types, and this is the same bullet points from earlier. So we know of only a few differences between the R Cobores and the dLHdCs. The first one is that they have slightly different oxygen isotopic ratios, wherein the dLHdCs seem to, in general, have a bit more oxygen 18 than the R Cobores. We also know that they have slightly different variation timescales, which may imply different masses of the stars. So if you have something like a flute, that's going to have a different variation timescale frequency than something like a tuba, which is much larger. And so that can imply different masses between the stars. And so those are pretty much the two main things we know. And what we can also see from this CMD here that I've taken from Patrick Tisseron's paper is that the dLHdCs, which are here in green, tend to be slightly warmer on the whole than the R Cobores do. And the R Cobores also look like they kind of tend to be a little bit more luminous than the dLHdCs do. So we have a lot more R Cobores over here at these brighter, as these higher brightnesses, and we have a lot more dLHdCs, which are kind of distributed like this. And so what we did was we made two target regions. We drew a box around them. So we have the R Cobore box here at the top, which has a bigger range in temperature, but a smaller range in luminosity. And then we have a dLHdC box, which has a slightly higher range of temperature, but smaller, and then a bigger range in luminosity. So these are our target regions that we're trying to get to with our models, and we're trying to also explain these two other things with our models as well. So when you model R Cobores or HDCs in general, there are a plethora of different types of modeling methods that you can use. All of them use our lovely code friend MESA. And here are just three types. So there's something called the engineered models, where engineered means we're doing non-physical things to make the star look the way we want. These are generally easier to create, and so that's why there's a whole lot of papers about these. And this is the one that I use, the one that I like. Sort of historically, and has come back into fashion a little bit, is these modified AGB models, and wherein you have an AGB that you then change all the abundances of. The problem with these, in my opinion at least, is that they don't really look like mergers. And so if we think that they're formed by mergers, then you probably don't want to use this model. But if you don't think they're formed by mergers, if you think they're a weird AGB star, you might want to use this model. And then we also have accretion models. The problem with these is that they no longer work in MESA. So this is where you have a white dwarf and you just accrete material onto it. This is by far the most physically motivated of the methods. The problem is just that it doesn't work in MESA anymore. And if you're interested in why, you can ask me later, because I do actually know why. And you can see they all have slightly different behavior up at the top right, which we call, the R Cobore box, which is the one I just showed. They all have slightly different behavior up here, but they all go to roughly the same region of the temperature and luminosity diagram. So like I said, I use the engineered models, and engineered models use non-physical processes in MESA to try to replicate the structure of a 3D hydrodynamical simulation of a double white dwarf merger. So we just do a lot of fancy MESA shenanigans, and hopefully we end up with something that looks like the hydro simulations. So here is one example of a hydro simulation from DN 2011 of a CO white dwarf plus a helium white dwarf, where you have the temperature distribution. The point here, and what we're actually trying to replicate, is that we want to have a cold isothermal core. We want to have a hot helium burning shell on top of that, and we want to have a big extended envelope. So in this case, you can think of this as the center just being the carbon-oxygen white dwarf, and everything outside of that is the helium white dwarf, which is just all mixed up and forms an envelope. So what you can do is you can make a normal star, you can change everything about it, including its temperature profile, and you can inject some heat at the base of the core where you want to, and you can make something that looks just like this. So we still have a cold core, cold isothermal core, we have a hot helium burning shell, and we have this big extended envelope out here after we do all of our MESA stuff. And what's interesting too is that you can choose your helium burning temperature by changing the amount of heat you put in here. You can also change the total mass, the mass ratio, all that kind of stuff just by choosing different, by editing your model. So they're very flexible. So this was an honors project done by my student Nikita Nikoltsev, which turned into a paper this year after he left the field. And what he did was set out to simulate different populations of mergers to try to explain actually the dy-pers and not the dLHdCs. But he by accident explained the dLHdCs. So what he wanted to do was try to test different total masses and mass ratios to see if we could actually move them. We wanted to move them rightwards. That clearly did not happen. But we moved them this way. And so what these points are is that you can see the track here in the background. The points represent this peak here, which is where the model spends most of its time, of its life. And so that's where we're most likely to observe it. And so the size of the points here represents the mass ratio. So bigger size is bigger mass ratio, which means that the stars are closer to twins. And so what he found is that for stars with lower total masses and higher mass ratios, you actually decrease the luminosity and move them slightly leftwards in the temperature diagram towards this dLHdC region, which was really interesting to us. So keep in mind that for a luminosity and temperature sense, what you want to have is a lower total mass and a higher mass ratio. Now that luminosity is related to the core mass, which is what he found. The luminosity of the HDC is set by the core mass, which is set by the carbon-oxygen white dwarf mass pre-merger. This also in turn affects the HDC star lifetime as well. So this affects both things, but of course this is not a new result. People knew about this before. It was just kind of nice to see it look so pretty, if you will. So the other thing that we know about dLHdCs is that they have slightly more oxygen-18, or they have a slightly lower oxygen isotopic ratio. And so when he looked, he found that the lower total mass models and high mass ratio models, which are the same ones that are in the right HR diagram location for the dLHdCs, also have more oxygen-18 than their counterparts. And so you can get both of the things that define dLHdCs as distinct from R Coronae just by changing the total mass and mass ratios. So that was really exciting for us. So to summarize, we've got these, differences between all the stars, and in fact, we can explain all of them except for the dust just by using different merger populations, different progenitor mergers, at least the ones that we know of so far. And the conclusion that you can take from this is that the dLHdCs seem to be from lower total mass and higher mass ratio double white dwarf binaries. But of course, there's some lower limit as well as to how far you can go. So that's been really nice for us and has been really helpful. So that's all that I'll talk about with the formation mechanism. Now I'll talk about the dust properties and something that I've been working on now and I'm still kind of working on, which is an ongoing question. What's going on with the R Coronae dust? So R Coronae, especially R Coronae itself, they've been known for a very long time. In fact, R Coronae was discovered in 1797. And so it's been known for over 200 years. But actually, when we talk about studying dust, a lot of the old work really focused on measuring the temperature of the infrared dust shells rather than looking at, say, how often is dust produced, how many times, how long are the puffs, if you will. This kind of infrared dust shell work has been done for many stars. But something that came up, something that's been interesting to us and has informed our current model of the dust is that even though most of the stars have these dust shells, so these infrared excesses here, some of them, such as XXCAM, one of my favorites, has an infrared shell showing that it has dust, but it has no declines in its 68 years that we've been observing it. You might call this a decline, and I might be convinced to agree with you, but it's a little bit small. So what we think is happening, at least with XXCAM, and what this kind of analysis tells us, is that the dust is probably not forming in shells or sphericals. It's probably clumpy in some way. And for XXCAM in particular, we may very well be seeing the star Polon, where the dust is forming around the equator and sort of moving away from our line of sight and not forming in front of us. And so our best idea of what is happening with the dust is that the dust is forming in small puffs, and these puffs form around the stellar equator-ish. We think they form close to the star, and then they are just pushed away, and as the cloud moves towards us, it gets bigger, covers the star, sometimes covers the dust around it. And eventually, that dust will move far enough away that it will become optically thin again, and then we can see through it, and it will rise back it will recover back to its maximum light. But our understanding is that we will only see these obscurations of the star if the puffs are actually in the line of sight and coming towards us. So if they're coming off the sides, we probably won't see that as a decline, we call them. So recently, my collaborator Patrick Tisserand discovered basically six-tupled the sample of known R Coronae stars because he actually looked for them using the infrared colors. And so now that we have so many more R Coronae stars, it was finally time to look for trends in the dust production properties. And so in order to do that, we collected as much photometric data as possible. So R Coronae Borealis itself has a very lovely light curve from dLHdC, which is 227 years long. So that's perfectly good for R Coronae itself. But a lot of these stars are not observed by dLHdC. So we collected from all of these other different surveys here. So here's an example of a more typical star where you have, in this case, 10 years of data, but you have a lot of different photometric surveys that you can pull from. And these light curves will be sort of whatever you can get is whatever we'll use. So we used as much data as possible. And then we wanted to go in and we wanted to actually count and see where every single one of those declines are. And in doing so, we can measure 6 different properties of the dust declines. And I'll go through each of them really quickly. The first thing we want to try to figure out is the decline frequency. So how many times are stars declining per year? Or how many dust puffs are they making per year? This one's simple. You just count the number of declines. You divide it by the baseline, you get frequency. We also want to know the percentage of time that a star spends in decline, which is very similar, but has a component of the actual length of individual declines. We want to know about the lengths of individual declines as well, but for this one I actually want to point out something special, which is that sometimes you have a decline in a decline. We call these nested declines, so this one here is nested inside this one. And these are actually really difficult to deal with sometimes, and I'll try my best to be clear about when I'm including them and when I'm not, but just know that that happens. We also want to know the depths of declines, if possible. So if possible means if you don't have the full decline, we don't count those. And if it's a nested decline, we also don't count those, and that's because you have a recovery occurring while a decline is happening, so you don't know about the actual dust puff itself. It's sort of a combination of multiple puffs. We also want to know about the slope of the onset. So here that's this part down. Again, we don't measure the nested declines or anything where we don't measure the beginning. If we don't have the end, we'll still count the slope, because what we actually care about here is measuring the formation time scale of the dust. How fast is the dust forming before it's fully obscuring the star? And the last one is the delay times, or the wait times. I actually got this idea from solar flare research. So this is what solar flare people do, where they count the amount of time between successive declines, and then they turn that into a cumulative distribution, and they can look at it that way. So that's what they do. So let's go through each of these. The first one I want to talk about is the activity indicators. That's the decline frequency and the percent of time in decline. These are very similar measurements, but we have a wide range. We see basically a huge range of all of these, but as for decline frequencies, most stars have 1 or less declines per year, and only a few stars have more than that. But for the percent of time in decline, we have just a big range all the way from 0 to 100% of observed time in decline. We do have quite a few stars that have 0, 0. That's because their light curves are very short, and they didn't go into decline in that time, and so there's not much we can do about that. If ideally you would have long light curves for all these, but we just don't. Now we can also look at these as a function of temperature, which actually makes it more interesting, which you can see that the cold stars here, so the HDC 7s, have more frequent declines, and they also spend more time in decline in their light curve. This makes sense on a condensation temperature argument, wherein the cold stars should be more likely to form dust. What's interesting about this is that the dy-per stars, which I said might be cold arcobores, according to some people, don't follow this trend. So they don't look like cold arcobores in a dust sense. We don't know why that is, but it's something we found here, which we weren't necessarily expecting. So the decline frequency and the percent, this one. So what I want to say is that the average activity, these decline frequency and percent of time in decline are average measurements over the whole light curve. And that's kind of a weird thing to do, actually, if you think about it. Because for Arcobore itself, which here's its 200-year light curve, it goes through phases. It goes through phases of time where it spends a lot of time in decline. And it has some phases where it goes through, not very long in decline. And so if you only had 10-year light curve, it might be these 10 years, but it also might be these 10 years, right, where you don't have any declines. And so this is just something to keep in mind, or something that we have in our minds, which is that we're thinking of averages here, and that's not often going to tell the whole story of a star, but we're doing the best we can. For Arcobore, you can see that there's actually almost like a median here of the percent of time in decline. And when you do the average over this long light curve, you get something that's around 30-ish% of time in decline, which is consistent with what you would see in this way. So the activity indicators that I showed before, the decline frequency and the percent of time in decline, are related. They're related by the length of decline. So if you divide them out, you just get a time, which is the length of a decline. So they're related to each other, and they're related by a median decline length of about 88% of a year, or roughly 1 year, if you want to get loose with it. And that's the same regardless of if you use these average indicators here, or if you actually go in and you measure the length of every decline individually, and you make a distribution, which is this histogram here. You get the same, roughly the same estimation for the average length of a decline, regardless of how you measure it. What's also interesting is that the declines themselves seem to be distributed in a roughly log normal distribution around 1 year. I have no explanation for this, but it is something that we see. And we're not necessarily sure what is so special about the 1 year time scale either. Why would a decline be specifically 1 year long? As for the depths are a very biased measurement, as you may have guessed. They're very biased by the faint limits for different telescopes. So if your star is only 4 magnitudes above the faint limit of the telescope you're observing it in, all of the declines you measure are going to be 4 magnitudes, right? But if you look at the brightest star, such as Arcobore, you can actually maybe see the whole decline in this case. So Arcobore's deepest decline is 8.85 mags, which is 99.97% reduction in flux. Here you can see it in flux space, where you can actually see all of these little structural things down here are very, very small when you look in flux percent. So we're not seeing very much of the star, if at all, throughout this decline. And what we can say, even though our decline depth measurement is very biased, is that the vast majority of declines obscure more than 95% of the star's total flux. So they're pretty much covering the whole star when we do see them, generally speaking. All right. Almost through the dust stuff, but the decline slopes are also very interesting to us. So this is telling us about the dust formation timescale. How fast is the dust forming in our line of sight? So I measured this for 6 stars, which had very long light curves with a very well-sampled light curves. So these are all from AAVSO, these really nice light curves. And then I also did it for dy-per, because we had to see what was going on with that. So what we see is that for all the Arcobores, we have varying distributions of the amount of flux blocked per day. So you can think of this like if you block 2% of the flux per day, it takes you 50 days to get from 100 to 0, right? So that's roughly what we're going for with the time scale. And so these stars, the Arcobores, decline faster, generally speaking, than dy-per does. And you can actually see that here if you look at these two 20-year light curves from WVSO, you can see how fast the decline goes down for R Coronae in each of these different declines. And then for dy per, you can see that it's a bit slower to go all the way down. So it has a slower dust formation timescale. A subtle difference as well is that dy per's declines are also a little bit shorter, so they don't go quite so deep as well. We call them more symmetrical when we talk about them. And as I said, these slopes indicate the dust formation timescale, which is roughly 30 to 50 days for R Coronae, and this is consistent with R Coronae carbon dust nucleation models, such as the one from Voitke in 1995. And so it seems consistent, at least with the models that have tried to attempt to explain dust nucleation in R Coronae, at least on a timescale sense. And then lastly, we also looked at the wait time distribution. So this is interesting to me, at least, in that we looked at 3 stars with very long light curves, and 2 of them look the same and 1 of them looks different. And so for R Coronae and SU tau, these are well represented by a Poisson distribution. So just to explain what we're looking at a reverse cumulative distribution of the wait times. So that's the difference between the decline onsets. How long do you wait before the next event happens? And we can represent that by a Poisson distribution, which is this dashed line here, wherein the dashed line that we've drawn is not actually a fit, it's a prediction by the average decline frequency, which we measured by counting the number of declines. And so the R Coronae and SU tau are well described by just a simple Poisson distribution, where the Poisson rate is the rate of declines that we see. But RY-Sag, on the other case, is different from the other two, wherein it has a buildup of wait times, where it has a lot of different declines that happen at the same time from the last one, right? And it has these sort of 3 buildups, if you will, and I've drawn some lines here to draw the eye. But once again, these aren't fits necessarily to the data. What I've drawn here are integer multiples of RY-Sag's pulsation frequency, where I just picked the one that aligned with the buildup itself. And what this may be implying is that for RY-Sag, its dust production seems to be tied to its pulsation period, as opposed to R Coronae and SU tau, which don't have the same property. But maybe RY-Sag is special. So RY-Sag has been known to be, it's a famous R Coronae, it's one of the brightest. And RY-Sag is also known for its especially strong pulsations. You remember maybe from when I showed the pulsation slide earlier that RY-Sag has these really big, large radial velocity pulsations, which are quite large and quite beautiful, if you will, quite obvious. And RY-Sag has also been observed to have shock waves in its atmosphere from these pulsations. So here you can see on this titanium line, you can see the shock here happening, and then the radial velocity of the line changing about this mean here. And so shock-driven winds shock-driven dust formation is a thing that people talk about all the time. And so that's what we believe most of the R Coronae are forming dust by, but then why would RY-Sag look so different from the other ones is a good question. And so it seems that RY-Sag is being driven, its dust production is being driven by its pulsations, but we're not sure with the other 2. So to summarize the big long section about R Coronae dust, what have we learned? We've learned that cool stars have more dust, they're more active. We've learned that a typical R Coronae decline is about 1 year, and it's distributed roughly log normally, but we don't know why, 1 year specifically. We know that most declines obscure 95% of the stellar flux. That probably just tells us something about the location of the dust in relation to the star and how big it is. We know that the dust formation timescales seem to be consistent with carbon chemistry models, which is just a good check on those kind of things. And we found that there might very well be 2 distinct dust formation mechanisms based on how strong your star is pulsating or if it isn't. But many questions remain. Here I've listed only 3, So what is the dust formation mechanism if not pulsations? So it could be something like the convective cells are producing dust, but that's another question. Why is the dust forming only over parts of the star? So why is XX Cam not going into decline all the time? Is not really an understood question. And as I said, why are the typical decline lengths about 1 year? We just don't really know. And so I'm going to end here on my fun summary slide, wherein I hope what I got across in all of this information is that HDCs, hydrogen-deficient carbon stars, are really interesting stars. They're unique. They show interesting abundances. They're unique in that they are an exotic formation channel. They're formed by double-white-dwarf mergers of varying total masses and mass ratios. We see that the dusty stars show a lot of differences based on their temperature, and we can see we're starting to get an idea of what might be going on with the dust, but a lot more work is yet to be done. And there may be 2 dust formation mechanisms for these stars. And normally on your last slide, you put your beautiful James Webb picture, whatever your best picture is. So I don't have that. What I do have, though, is some lovely Herschel images of our favorite stars, SU Tau, R Coronae, and RY Sag, my friend here, where you can actually see the little dust nebulae around these stars and the beautiful bow shock here. So I'll leave you with that and take your questions now. Thanks for listening.
Thank you. So I have a question about, I think it was XX Cam, which I knew because it was on the previous slide now, where you suggested that it could be spitting out dust sideways and we're looking at it full on.
Yep.
But wouldn't we still see the cold dust that has moved away because it would still be within like telescope field of view mostly? Like it should still be cold dust even if it's not in the line of sight.
Yes, but it wouldn't obscure the star, so it wouldn't have a decline.
I mean, you're saying there's not much of a dust shield there as well, right?
Yes. We can maybe talk more about this later, but even if you were to say, like, how long ago did this happen, we didn't see a decline then. But I do agree it is a weaker dust shell than like these ones here. I guess the point that we want to know is, like, how was it producing dust at all, and we never saw it.
Thanks for the great talk. I had a couple of questions. One was, for example, for the R Coronae stars, for how long do you actually expect them to be in the R Coronae state, right? So sort of trying to do an estimate just from the luminosity and the amount of helium that they likely have in the shell to burn, I was guessing 10,000 to 100,000 years. Is that roughly sensible, or is it much?
So I actually have a plot on this. I'm a backup slide fan. And this is actually not the ideal way to look at this, but what these here are the same models that I showed from the dLHdC paper, where what you're asking about is from here to here, where it crosses the line. That's what we call the R Coronae lifetime, so how long it spends within the box. And so most of the stars are between, in this case, 200,000 to 400,000 years that it's spending in the R Coronae phase. But the thing is, you can change this number by changing the mass loss that happens at the tip there, and you can make this much shorter if you want to. So it's a bit inconclusive, but until we understand how much mass is being lost there, we don't know. But most models predict between 10 to the 5 and 10 to the, around 10 to the 5 years. So you can get a predicted total number of stars if you use the birth rate from Amanda's paper of on the order of a few hundred stars that we expect in the galaxy.
So very spectral. Awesome.
Yeah. But this is also related to the core mass, right? So the different core masses have different lifetimes as well.
Well, I have a question, but it's about that Zhang paper from 2012. So why can't, 2014? Why can't they, sir?
So, yeah, that's a great question. So I asked Sunny Wong this question at the Mesa Down Under workshop because he would know the answer. And the answer is that in the old accretion, in early versions of Mesa, they actually had the wrong energy conservation equation. They were missing a term. And you actually might notice there's still options in the Mesa Endless where you can turn that term off to go back to the old version. But once they added in the right term to get the right energy conservation equation during accretion, this broke, because basically what happens is that your time scale gets excessively short and then you just don't converge anymore. And so that's the problem. And I'm working with Sunny to try to fix it so that we can do accretion models again, because I think that would be really awesome. And that's, of course, what Sunny Wong does. But we'll see.
Thanks.
Yeah.
Sorry, one more question. I apologize. So I remember reading somewhere that one of the issues for the white dwarf merger model for Arco-Bohr stars is that some of the Arco-Bohr stars have lithium, and it's hard to see where that would come from in the double-white-dwarf merger model. So, so what is that a real issue, and what's the explanation?
It is a real issue in that we cannot explain why any Arco-Bohrs have lithium. There are 4 stars with measured lithium abundances, one of which is Arco-Bohr itself, so you kind of can't ignore it. And we've done like a pseudo-lithium calculation using the low-resolution spectra that I did the classification on, but you can't like measure an abundance from that, so we don't have abundances on those. And it looks like about 30% of Arco-Bohrs and dLHdCs have lithium lines, and honestly, we don't know why. The models that we make cannot replicate the lithium because of, they can't replicate the lithium, and we don't know why it's there. And we really don't have an explanation. It is a problem, but I will say also that the final flash models, so the ones that the double white dwarf mergers were against, also can't create lithium, and so it's kind of just a problem, full stop, no matter which model you believe.
I think Yoshi, you had a question?
Thanks for the talk. You mentioned that you had a stellar nemesis.
Yes.
U166.
Yes.
And it had like a stronger barrier.
Yes.
Is there anything else that's strange about?
There is.
Yeah.
There is so much.
Okay.
I don't have a plot of it, which is really upsetting. Normally I put my stellar nemesis plot on here. But yeah, so it has strong barium. It has strong strontium. Like, it has very strong barium from what you saw in the equivalent width plot. But what also makes it look very strange is that, do I have any spectra nearby? So it's a cool Arco-Bohr, but its spectrum doesn't look like any other cool Arco-Bohr. So instead of being like slanted, as a cold star should be, it's like rounded, which is very strange. I think that it's in decline, and that we've just observed it in decline, and that it's not actually a dLHdC like Patrick claims, but we don't see an infrared excess as well. It just looks really weird. I can show you some plots later. It's my nemesis and I hate it. Every plot we make, it is in a different spot from where all the other stars should be. I actually have a suspicion it's not an Arco-Bohr at all, so I don't like that star.
Then maybe follow-up, if that's okay. Have you observed other spectra in decline, if you think that's...
There are a lot of spectra in decline, both by accident and on purpose. And it doesn't necessarily look the same because it's not quite so reddened as we would expect. And it doesn't have any emission lines, which we tend to see in decline spectra. But it does look like all of the other lines are very veiled, which is why I maybe think it's in decline.
So you mentioned mass loss before. Is there some sort of approximate or ballpark amount of mass loss that you see and or expect?
No.
Or don't want?
Yeah, short answer, no. In the models, we just use a blocker wind, which is, not ideal. But Josiah Schwab wrote a paper on this where he attempted to make a mass loss law to put in his models. I don't remember offhand if he used physical constraints or not, or if he just wanted it to look like an Arco-Bohr based on like opacity differences. But I can look at it for you. The short answer is no, we don't really know, but Josiah has done a little bit of work on that.
Of the stars that you have that can emanate data for the variability, how much of them are sort of periodic, and how much of the variation is stochastic? What's the fraction of stars?
Of the data, I honestly haven't looked. And so I haven't looked yet. This is a next year thing. Next year is when I'm really going to start focusing on pulsations. The reason we did the declines first is so that we could mask them out and then have the maximum light spectra. So if you find all the declines first, then you can very easily remove them. And so I haven't done it yet, but I've been able to find a pulsation signal in 2 stars out of the like 20 that I've tried. The dLHdCs are a different beast altogether. Those ones are a little bit easier, but you tend to have shorter light curves, and so the spectral resolution is kind of bad. And so that's about where we're at, but I'm hoping next year to really dig into that kind of stuff.